Hi everyone, my name is Yuhsin Tsai from University of Notre Dame. In this talk, I want to discuss about the curvature perturbation sourced by first-order phase transition. And I'm going to explain how to understand the behavior of the curvature perturbation using the finite statistics of the phase transition bubbles. This discussion is based on a paper I wrote with this fantastic collaborators. And then if you have any questions, you can either ask me during discussion time or take a look at our paper. Okay. So usually when we talk about the first order phase transition, we care about the gravitational wave spectrum it's produced and what's the tensor mode perturbation. But in this work, we want to ask how does the scalar perturbation looks like, or just the curvature perturbation that looks like, which will also change the cosmological signatures, and which should have an even simpler form than even the tensor mode perturbations. We know there should be scalar perturbation because phase transition is a pretty random and violent process, so it's far from homogeneous. So to set up scenario for the discussion, let's consider the phase transition happens inside a dark sector, okay, where the only signal we are going to see from the fluctuations in the phase transition coming from the mediation through the gravity. Okay, so from the gravity perturbation that changes all the other particles and changes the cosmological signatures. So it's a challenging process to study because it has no direct coupling to the single model particles, but cosmology is a great place to look for such signals. Okay. I'm going to take the standard parameterization of the phase transition, which is this bouncing action with the parameters that correspond to the linear order perturbations of the bouncing action in time. And bouncing action is a thing that describes the tunneling probability from a false vacuum to true vacuum during the phase transition. There are three important parameters in this discussion. One is the phase transition time in the comoving time, or the phase transition temperature, which is the Snell model radiation temperature when phase transition happens. Um, um, but the actual duration of the phase transition can be much shorter than this time scale, okay, which is determined by this beta here, which determines when will the things on top of exponential be a very large negative number or start to be less negative, so the exponential start to grow. So that time scale is set by this beta inverse, which is the duration of the phase transition, which also sets the length scale of the bubble separation or the bubble size, okay, together with the wall velocity. Okay. And in the end, we want to know how much energy densities can be stored in the dark sector and then can be released during the phase transition process. So when we're comparing to the experimental data, we want to set upper bounds on this energy density ratio between the dark radiation and the total radiation energy. Assuming taking a simple assumption that all the latent heat from phase transition gets into the dark radiation. And in this case, we will also assume it's some kind of a supercooled scenario that the dark sector is dominant by the vacuum energy. Okay. Just to simplify the calculation, in our paper, we write things down in a more general way. But for this discussion, let's just keep it simple. So all the energy of the vacuum energy difference just goes into the dark radiation energy density. Okay. Okay. So that's the general behavior of the phase transition and then also the energy density and things like that. But how about the perturbation? So let's first consider the fluctuations in the phase transition time. Because once we know the fluctuations in time for each point in space that turn into the true vacuum, we can relate that into the energy density perturbation, or later the curvature perturbation. So to do that, we want to calculate this two-point correlation function of the phase transition time fluctuation for individual points, separated by some 1/k scale, some co-moving wavelength scale. Okay. So we calculate this carefully in our paper using the impressive work developed by Ryosuke Juno. By the way, he is giving one of the review talks, so can be related to some of physics I'm talking about here. And for this calculation, we just need to figure out the geometry of the four-dimensional light cone of the bubble. How do they convert the different points into the true vacuum at a different time? Okay, and that can either be given by a single bubble that first hit one point, then hit into another point, or I can have two separated bubbles that first hit one point then the other. And we basically take into account the probabilities for each cases to happen, and then calculate the standard deviation of the time. And by doing so, we can obtain a power spectrum of the phase transition time. And once we normalize the spectrum in certain ways, we can make this power spectrum versus the co-moving wave number with certain normalization to be a model independent power spectrum. Okay, so as long as your model can be described by some gamma exponential beta t type of thing, you only need to translate your number into certain the normalization we give you here, and then you can find out what the spectrum is. The power spectrum on the left-hand side of this around the peak, which is basically set by the bubble size, will have a well-defined power law. Okay, which I will discuss a bit more about where does this parametric dependence come from, with some beta over h factor I mentioned before, and then k times the phase transition time cubic. Okay. But on the right-hand side of the spectrum, this is for the length scale that's smaller than the bubble size. Even if we can estimate the time fluctuation, it's very difficult to keep track of all kinds of nonlinear corrections to the energy density of the dark sector. So we will be mainly focusing on the co-moving wavelength that's much larger than the bubble. Okay. So where does this parametric dependence come from? Okay, so just to give you a quick idea, because it's a short talk, and then I am happy to explain more of this afterwards. Whenever you have phase transition probability density written in this form, you can parameterize it by measuring the time in the unit of beta inverse. By doing so, you can always rewrite your phase transition probability in this universal form when you measure the time in steps of beta inverse. And then that means that no matter what kind of phase transition microphysics model you have, the probability distribution for the phase transition to happen as a function of time always follows the same distribution. Okay, and then when you are looking at enough chunk of beta inverse space, the patches in the sky, and which is basically the size of the bubble right before the end of phase transitions, then you can find the standard deviations of the time when each patch went into the true vacuum. Okay, it would be some fluctuation around some average. And that fluctuation would basically be some 1/√m of the number of patches that you have. And you can calculate what's the number of this beta inverse lattices or boxes that you have by taking a ratio of the co-moving volume to the size of the bubble-sized patches that you have inside the volume that you want to do a cosmological observation. Okay. So by writing the time back into the physical time, and then doing this 1 over root n statistics, you can recover the form of the perturbation to be what we derived from a careful calculation. And also including some details like the wall, the size of the bubble also depends on the wall velocity and things like that. And this result in the end is only about the factor 3 smaller than the careful calculation. So all this parametric dependence coming from that 1 over root n statistics, that's all. Okay. And once we get the phase transition time fluctuation, we can use it to get the curvature perturbation from the phase transition, with the idea that even though initially, assuming instantaneously a phase transition, the energy conservation will make the initial energy inside the bubble to be the same outside the bubble, which is just a rough idea. I mean, in the beginning of the bubble nucleation. But what this means is that initially, right after the region got converted into true vacuum, because of energy conservation, the total energy in the patch A will still be the same as patch B. You just change the vacuum energy into radiation with the equal amount of energy. So you have isocurvature perturbation in the beginning, but you don't have curvature perturbation. But because radiation, dark radiation redshift faster than the vacuum energy, so soon after that, this bubbles, energy density in the bubble will become smaller than the regions that remain in the false vacuum. So this will make the total energy of the patch A start to be larger than patch B if there are fewer bubbles being produced, so that you start to convert the isocurvature perturbation into the curvature perturbation. There are different ways you can calculate the curvature perturbation, and we show different ways in the calculation in our paper, and they all give the same result. Probably the simplest way to do is to use this expression of the curvature perturbation, and then by taking a spatially flat gauge so that the metric perturbation is 0, so that the curvature perturbation is given by the fluctuation of the dark radiation energy density, which is sourced by the fluctuations in the phase transition time with a certain relation. And there are other ways that you can do the calculation. If you're interested, I can tell you more about this afterwards. Okay. So once we are done with the calculation, we get a power spectrum to be the sum of the adiabatic perturbation and the curvature perturbation from phase transition. By the way, I forgot to correct the typo here, so there's no 1/4 here. Okay, and this is about factor of 3. Sorry about this. But once you get the spectrum, we can compare this to the cosmological data, and then ask how much energy density I can have in the dark sector, because this large perturbation from the phase transition will be diluted by the fraction of the energy density in the dark radiation versus the Snell model radiation. So that's the FDR square. So I can set the upper bounds on this. Okay. So the typical constraints on the dark phase transition is this delta ineffective constraint, saying that if you have a phase transition with some energy, even if later released into the dark radiation, you cannot have this energy density fraction above certain level from the existing bound. So these are the existing bound, okay? And in this context, we will focus on phase transition going between EV to the GeV scale, okay? Even though this is a much lower energy scale comparing to like the electroweak phase transition, it's still an interesting region of the phase transition temperature to consider, both for the possible applications for the pulsar timing array signals, that's about the 10 MeV scale, or there are some models, one called the new early dark energy models, they're trying to use the cosmological phase transition to explain the H0 problem. Okay, so these are interesting implications of phase transition happen at the late time. By the way, when looking at the signals, we shouldn't pay too much attention on the delta N effective constraint at the same time, especially for NEDE. We do take all the cosmological. They do take all the cosmological data into account, so it's not excluded by this. Okay. So having a large curvature perturbation from the phase transition can modify different type of cosmological signals, including the CMB or the large-scale structure. You can enhance the matter power spectrum for certain K modes, or you can introduce the CMB distortion because you are going to heat up the photon baryon plasma. Because it's a short talk, let me just show you what we have in the end for both the existing exclusion bounds and the expected future sensitivity of this dark sector phase transition from the scalar perturbation constraint. Okay. And this is a plot on the constraint of the energy density fraction of the dark sector versus Snell model versus the different phase transition rate shift and the phase transition temperature, the temperature of the Snell model sector at that time. The CMB and the Lyman alpha constraint can already set upper bounds on the curvature perturbation. So we just take the bounds given by the Planck analysis, and then we can exclude this region. The exclusion bound depends on what's the beta over H dependent size that we have, because when we have a larger beta over H, that means the bubble size is smaller and taking more statistics, so the standard deviation is smaller, therefore the smaller perturbation. So that's why the bound gets weakened when the beta over H is larger. And the yellow region comes from the CMB distortion constraint from the FIRAS measurement. As you can see, we already can put bounds with a very interesting application to these new early dark energy models, and forcing the new early dark energy phase transition needs to be above, at least with the beta over H to be larger than 400, which is already slightly larger than the usual dimensional analysis result, which is about the order 100. Okay, so it can already provide some useful constraints to the model. But I have to say that the paper, I mean, from these authors already consider this type of constraint and then trying to use some more involved mechanisms and trying to make the beta of H to be very large. But the scalar perturbation bound does provide useful constraints for that. And then if we do have this more ambitious experiments that we can have in the future from like the CMB distortion measurements, if we can be sensitive to the energy density fluctuation to the 10 to minus 8 level, we can set a pretty strong constraint and push the constraint to a much higher temperature. Okay. Or if we have a very good pulsar timing array measurement, and given that a large curvature perturbation will produce mini dark matter clumps and changes the phase of the pulsar timing oscillations, that may be able to set a bounce or set a very sensitive probe to these curvature perturbations. So then that would be very interesting. Okay, let me summarize. First order phase transition generates superhorizon, isocurvature, and curvature perturbations, and they directly correspond to finite bubble statistics. So I show you the bound and the future sensitivity, and then that will set a very interesting constraint on the first order phase transition. And I highly encourage you to also look at a talk I'm sure will be better than this one from Aurora, talking about also the BMO signals from the first order phase transition. Okay, thank you very much, and we can discuss more during the discussion.